So let's continue on with the slides. Hey, tree traversal. Okay, we must start at the root node. We have two choices. Visit the node first or visit the subtree first. I guess you didn't think about this, but let me...
Why would you go to the subtree first?
Whoa, 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 whoa. Let's go to the board. Let's erase all this extra stuff we added. How are we going to print? Well, what's the order of printing?
Whatever you want it to be.
Probably you'd want it to be like least to greatest.
Least to greatest. So what number should it be? What number should it print first?
-30.
The leftist of
And
the
then
left.
the leftist of the left. And then we're going to go all to the rightest of the right.
English. Well, if there's no more left to that left, you go to
Oh, I was
the
waiting
right.
for someone to do a political comment. So the leftist. No? No one?
I hate
We don't care about politics.
I don't really understand it, so I just...
You don't understand politics?
I
Oh, no,
don't
no,
either.
it's easy to understand.
They're all wrong.
Well, yeah, obviously.
Everyone.
It's really just watching them get angry at each other and act like children. So you have to sit back and just laugh. That's
It's
the
like watching WWE but without the fighting.
Right, without the fighting.
So
That
it's
part I
even
get.
worse than WWE.
It's just
Yeah, at least they
Less
take out their anger.
entertaining.
Yeah.
Listen,
It's
I
what
don't
they're
know.
arguing
Sometimes-
about.
I don't know.
Yeah.
The current president knows how to troll. If I have to give that man any credit,
Why
he
does
knows
he
how to
still
troll.
have a Twitter, is my question.
Oh, this is Twitter.
Sometimes I think he just says things to just provoke people.
I thought they were
Well,
gonna
yes,
like
that's how he
block
rolls.
his Twitter.
He's like, you
block
know
other
what,
people
screw
from
you,
his
I'll do what I
Twitter.
want.
No, that's it. And then he uses small words. Oh, man.
He uses the same words over and over and over.
Oh, yes.
I
Which
never
one
know
was
his
it?
name.
Oh, he's this one, right?
Yeah.
Yeah, he's that one. Not the thumb pusher.
Which one's the pump?
That was Clinton.
Oh.
And then, what did Obama do? He just did the yes
Same
we
thing.
can. Oh, he did the thumb pushing as
Yeah.
well? Okay.
What is thumb?
The thumb,
You're
the
like
elevator,
that.
because I'm lifting you up.
Uh,
He doesn't want to do the peace sign because that was something bad. You don't want to do this because that means something real bad. And then,
What?
If you don't know, it doesn't matter.
yeah. What?
I said 2.
How come?
Oh, this was next.
Yeah, this was Nixon,
Oh.
and that's but doing it the other way was bad. I forgot what that meant. Oh no. Yeah, never mind. Anyways, so the leftist of the left, and then we'll finally get to the centrist, and then the righty right.
The righty right.
So you do the leftist of the left, and when there's no more on that left side, you go to the right, and then you go to the leftist of that side.
Yes, and you keep. All right, great.
So the lefty left and the righty right?
Righty right.
Okay.
Now, how to code this, no clue, but
Oh.
it sort of makes sense.
Okay, we got that. By the way, that's called the in-order traversal. You traverse the left subtree until you can't go down the left tree anymore. Then you print your node, and then you go to visit the node, aka print it. Then you traverse the right tree, which is in order, which means you go down the left tree. There's the hard way and the easy way. Which would you prefer?
The easy way.
Really? Are you
Which one
sure?
are we
Oh,
using?
wait, never mind. If we have to use the hard way, then.
I will never make you do this the hard way because that is dumb.
Then the
Wait,
easy
then why
way.
would we ever use the hard way?
You don't. Why would you make things harder than they have to be?
You do it all the time.
When?
It's
I do it all the time.
When have I done that? I have made so. Okay, hold on. I take that back. The fact we're using C++ does make it harder. But besides that,
like object-oriented. Second thing right there.
well, implicit to using C++.
Oh,
What
the
is your
math teachers do
preferred
it all the time
language?
too. They're like, you must learn it the hard way, so that way you appreciate the easy way.
And then you
That's
get
kind of
it.
what we're doing with all these data structures like array. We could
Yes.
just use the standard.
Well, you're learning it, so that's why you're writing it. All right, so the way you do this easily is you make a recursive function.
Woo.
It's recursive. So what's the first thing we need to do?
A base case.
Base case. And what's the base case here?
There's nothing in the entire thing.
Which means that node is.
No.
All right. We could write this, but I'm actually super lazy.
If not,
you should turn, why are you trying to print this? There's nothing here.
All right. You ready? Everyone hang on. You got this?
Everybody got your
Else.
pants
No.
right?
If.
No. No.
Or.
Uh-oh.
What?
Call the function the left side.
Yeah.
Get left.
And if it returns,
No. And then we're going to also call it when it's done on the right side.
Okay, I get it.
And then, since we want to first go to the lefty of the left, that means you wait for get left to return. And so you'll, silly C out.
Nice.
Get val.
Mm-hmm. And we'll put a space just for funsies.
Just for funsies.
All right. So your print is literally print the binary search tree of the root, and then, did I forget something?
Did you forget something?
I must have forgotten something.
Semicolon?
No.
He put a colon instead of a semicolon.
Oh, look at that.
Yeah.
All right.
that looks pretty nice.
So how many lines of code is the difficult way? Like 100?
You gotta put it in a while loop, and then you gotta add it. You have to create a stack and push push everything on the stack, keeping track of where you are and where your node is, and keep.
Let's just not.
Thank you. Yes. You sure? I mean, we could spend another hour doing that, or we could just do it the easy way. Hey, whoa, whoa, whoa! All right, guys, think about this. Which way is easier, the recursive or the iterative?
Recursive.
First,
That's right.
Iterative.
The door's right there.
You fail. Automatically.
That's just an F right now. See?
F on left.
Again, this is probably the first, definitely not the last, but this is probably the first clearest example where doing something recursively is way, way easier. On binary search tree, you could do it the iterative way, and it's not too bad. But in this one, it is a complete difference.
So what's the big O of the printing function then?
O of n, because you got to jump to every node, right? So it's always going to be O of n since you have to print every node. All right, void test3. Let's create our BST. BST.
We can copy everything else and then print it.
I know, because all that stuff up there is for our node. So we need to add, what number do we want to add first? 5? Yeah, let's add 5. And then we added, I'm doing what I did, not up there, but on the board, 14, and then 2, and bst.print. Hey, let's see what happens. Errors. Oh, C out. No, I've already added
No,
my
you gotta
STD.
include them.
I have to include the IO stream STD. Let's see, root was not declared in the scope.
Oops.
Line 39, probably because it was called mroot. And we got some root was not declared in the scope. Probably because it was called mroot. We got some warnings. No return statement function returning non-void.
What?
You don't know about that? So we're on line 70. Oh, let's return false. Because it didn't work. Alright, so... Oh yeah, let's go. Hey look, 2514. Wasn't that right?
yeah.
Okay. Let's add some more. What came after the 2? Negative 30? And then,
-3.
was it negative? You mean 7?
Oh, I was looking at the tree, not at the top.
It has, make sure you maintain the right order, because the order you add them for our binary search tree will create a different tree. Because if I put the 5 over here, the root would always be 14. Where are we? Oops. 19,
And then
negative 3. All right, let's see what happens. Wow, we did it right the first time.
So is this one of the better searching ones then? Like better than bubble sort and all the other ones?
You mean sorting?
Yeah.
Well, oh, so I see what you're saying. So if we were to sort a bunch of numbers, what if we threw it all in a binary search tree?
Yeah, because it seems much faster.
So if you had an array of a bunch of numbers and you wanted to throw into a binary search tree, what's the big O of that? That's a great question. It's a beautiful question. So you have this array and you want to convert it to a binary search tree. Nice and squeaky. What's the conversion cost?
What would it be?
Well, O, you have for each element, that's one n, but then you have to call add, right? For each element. What's the cost of add? Log of it. Well, so worst case
So n log n?
is n squared. Average and best is n log n. So, yeah. So what you're saying, so in a way, yes, it's a quick sort, so to speak, unless it's the worst case, of course. But the problem is, you now have two data structures, right? You have the array and a binary search tree. Of course, memory is cheap, so it doesn't really matter unless you have a huge database. But yeah, the conversion is on average n log n. Okay. Now, oh, I know what I want to do. Could we have done the same thing for add?
Probably.
Let's go look at add. The rec stands for recursive. Okay, so if rover equals null or to add equals null, then we're going to return because that was pointless. Okay. If rover get val is less than 2 add get val, I'm just pointing out that there's a different way to do this. Then we go ahead and we set it, right? We do this. One, two, three, four. Now let's do this. 1, 2, 3, 4. Except for, so rover, so in this case, you're actually going to return, you're going to call add rec with rover dash get right and to add. So that takes care of going down, which one, the right side? Then we got to go ahead and do the left side. I'm pointing out that in this case, it doesn't really help too much. But in a way, it's cleaner. Whew. Okay, I think that's it. Let me find out. So a quick guard in case something bad happened. Otherwise, if it needs to go to the right and it's free, you add it and then return. Otherwise, you recurse. Otherwise, if it's the other direction, you add it if it's possible. Otherwise, you recurse. And so instead of doing a while loop, you have the recursive function up there, in which case you would just do add rec imroot comma to add, because you still need that guard for the first one. So in other words, instead of this whole while loop mess, not a mess, but while loop right there, he goes up and checks this one out. Notice that I didn't check if it was equal. If it is equal, then it's just going to exit the loop and get out. So let's go see if it works, because I just coded that real quickly. Use of non-static member function. Blah, 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 blah. What? Oh. Okay. It should still complain at me though. Or maybe not. No one told me that I put a T there because it's not a rectangle. Nope, there. It worked as well. Which one do y'all prefer? Ooh, that's a good question. Hmm? Depends on, no, asking which you prefer. Depends? Well, no, for as an add function, would you prefer the recursive version or the iterative version that we wrote down here? It depends on what? What does it depend? Your mood?
Pretty much.
Good answer. Good answer. I like it. All right, what did we miss? Oh, who's trying to do something?
Nothing.
Oh, just trying to mess. You're trying to fix something, aren't you?
No.
Okay.
Taking screenshots. That's all.
Oh, you're taking. I upload the code. I think. If not, tell me. Okay. So we did what's called an in-order traversal. There are other types of traversal, namely two others. One called pre-order and post-order, and we're going to do that and finish up for the day. So in pre-order, let me look. In order, you traverse the left, then visit the node, aka in our case, print, and then traverse the right. In pre-order, you print first, then go left, then go right. And then post-order, you go left, go right, and then visit the node.
Those two seem dumb.
They are and they aren't. Depends on what you're trying to do. So, let's do pre-order. So we'll do in order first, because that's the intuitive one. Obviously, you go all the way left, so it's -30, -3, 2, 5, 14, 7, 14, and then 19. Right?
You're a little off board.
All right, let's do the professional panning. Oh, yeah. All right, there we go. Nice and bouncy. All right. So what would pre-order be? Actually, I should write it on the other side so my arm doesn't get in the way. You visit, when you get to the node, you immediately print it. So we're at the 5, we print the 5. Then we go
Left and then right.
left
2,
2,
left, -30, left, can't go left, right, -3, and then 14.
You go down the right side.
then 14, because we popped back up.
7, 19.
Go. And then post order. It's the, by the way, this is representing pre-order, the pre-order in the way of how the binary tree is laid out, and post-order of the way the tree is built, laid out. Post-order, so you print on the way back. So left, -30, nothing there, come back up. Go to the right, -3, nothing to the left, nothing to the right, then you print -30. Then you're coming back to 30. Since there's nowhere else to go, you then print the 30. Come back up to 2. Don't print the 2 yet. Go right, nothing's there. Then coming back from the right, you print the number. Call to the left, now it's time to go right, so don't print it. Go to 14, go left, to the 7, go left, can't, go right, can't. Then we print the 7. What number's next?
19.
19,
14.
And 5.
5.
So it's like seeing what's the deepest thing in the tree.
Yeah, yeah. Yeah, on that side. Okay.
Would it be useful to use the other orders?
That's a good question. I can't think of it off the top of my head. I know they are used. I don't remember when. But how do we do in the code? Well, that's pre-order. And then post order would be right there.
Oh, look at that.
And we'll leave it in order. All right, how are we doing?